It's about 10 o'clock in the morning on Thursday, June 29th, 2023. So 2 more days of June left. And this is what the cow patties look like in this pasture. So they've been back here a week. I don't know how old that patty is, but that's Swiss cheese. The dung beetles have gone to town on that. That's what I saw of the patties that I did see. It's just full of holes. So I drove out here to where the cows are. It's kind of hard to see, but this field of flowers, there's a lot of trampling that's happened here. I'll just kind of show you like where I'm at right here. This is kind of a high traffic area. They like to come through here to move back and forth. I like to come through here to move back and forth. There's kind of a natural lane that runs back here to the gate, and it runs almost the entire length of the property down back to that corner. For reference, this was burned about 11 months ago. We had a big wildfire, a grass fire that burned everything. This is number 20. She's super friendly. She is fat. She doesn't have too many flies either. It's not too bad. So this is part of the thing that was burned. You can kind of see the tree line. There's still a little bit of evidence that there was a fire. Sometimes you'll see a tree with the black trunk or whatnot. There's kind of like a line that you can see from the ground to the bottom layer of the branches. I don't know if you can see it very well. I certainly can. So I think tomorrow morning, I think, I don't know. Should I move them tomorrow morning? I gave them a week back here. It's 20 acres. So it's a third of my 60 acres, and I've been doing a 21-day rotation on my, so that's 3 weeks on 60 acres. I think I want to give my ground a little longer to rest. I see some really encouraging signs that the grass is starting to really take off, but I think maybe we'll go back. I'll take a look at it Monday evening. See what it looks like. There's still tons of grass back here that they have yet to even look at. I don't think they've explored even half of this property back here. They've just been sticking to the trees and moseying around, hanging out, doing stuff. Hey, 20. Let's see if 20 likes to be scratched. Not really. So that's the story. I don't know if this is all my cows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. We're missing like 8 cows. So they're probably somewhere else in the trees or something. Yeah. Actually 7 cows, because the calf has yet to cross the property line. Look at that calf. 413 playing with the dog. Temperature, it's about 85 degrees. It's hot in the sun. Not like extremely hot. We've been getting temperatures near the hundreds for the past couple days. And humidity's pretty high. So it's not like an Arizona 100. It's a Texas 100. That said, my brother who lived in the southern part of Arizona, he says that he has yet to experience a hot day in Texas. Of course, to him, he's talking oven temperatures, where 120 is pretty typical for a summer in June. I know people say it's a dry heat, but if you talk to anybody from Arizona who's lived there, they'll explain to you why that's not relevant. Long and the short of it is that your sweat can only keep you so cool, so much cooler than the environment. Like 100 degrees on a very dry day is pretty nice. It's not that bad. You might get sunburned. It's kind of fun to play in the pool, but once you get to like 120, it's just unbearable. It really is. My goodness, my dog is freaking out. Anyway, there's something I wanted to add about temperature and climate and stuff, something important. So one of the there's some cows in the tree line there. They're coming out. One of the theories of global warming, the greenhouse effect, blah, 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 is that somehow the heat can reflect back. Like the heat comes from the earth, goes up in the air, and then reflects back to the earth, okay? And this is unphysical. The reason why is heat, first of all, is defined. There's a specific definition of heat. And heat is defined as energy that is transferred between two bodies due to a temperature change, a difference in temperature. And heat always flows from the warmer body to the cooler body. And when you get down to the mechanics of what's actually going on, you start talking about things like entropy. Okay, and entropy is a powerful concept. It's not a very easy concept to understand, but it's a very powerful concept. I'm going to try to explain it here in the next 5 minutes. So imagine, if you will, that let's take a checkerboard, 64 squares, 8 by 8, right? And you have one red checker, and you're allowed to put that checker anywhere on the checkerboard, right? And so that checker piece can occupy one of 64 possible positions. Now, at the fundamental level of physics, at the very basic, like the particles that are actually moving around, you don't know like why that particle would move from one square to the other, or how it moved, or anything like that. You just know that of the ways that you can arrange that one particle in that chessboard, that one piece, there's 64 possible combinations, right? If you were to have two checker pieces, then all of a sudden you get 64 for the first one, but then the second one can only occupy one of 63 places. So you're not going to allow it to stack. Wait, let's allow it to stack, so you can have two checker pieces on top of each other. So you have 64 squared possible ways to arrange those pieces. I'm a physicist. I don't like to do math, so I'm going to say 64 is about 100. So 100 squared, that's about 10,000. 10,000 possible ways to arrange those two checkerboard pieces, right? And if you have three pieces, now we're talking about 1,000,000, right? So we went from 100 ways to arrange this piece to 10,000 to 1,000,000 with just three possible particles, okay? Now, shift your view here. We're not talking about particles. We're talking about little packets of energy, okay? That energy can be allocated in any one of those 64 squares, or 100 squares, because we're rounding up to 100, right? So there's 100 possible ways to allocate one packet of energy. There's 10,000 ways to allocate two packets of energy. And there's 1,000,000 ways to allocate three packets of energy, okay? You get what's going on there, right? This is the way most systems that you're used to dealing with in the world happen, is the more energy you add, you get more and more ways that you can arrange that energy, right? Okay, now imagine you have two checkerboards, okay? On the one checkerboard, you have 4 pieces. On the other checkerboard, you only have 1, okay? Now you can randomly move those checker pieces to any place on either of the boards. What is the most likely outcome? A, all the checker pieces are on one checkerboard. B, the two checkerboards have equal pieces. Or C, nothing moves at all, right? Everything stays on the same checkerboard. The answer obviously is B, right? And the way you do that is you look at all the possible arrangements of how you can allocate those checker pieces on the checkerboards, right? So with two checkerboards, let's say now that we have 50 squares on each checkerboard, just because I want to do 100 instead of whatever else. So there's a 50% chance that each packet of energy can be on either checkerboard, right? Because they have the same number of squares, right? And so the most likely outcome is that it kind of allocates evenly between them. It might be off by one, like one might have 1 or 2 more than the other, just because of random chance. But typically, it's going to be equal, okay? So this is what's going on when you bring two bodies into thermal contact with each other. What that means is that you're allowing the energy from one system to move to the other system or back, okay? So the energy can move either direction, and the truth is you can't know. Like, there's no way we can get in there and watch and see these particles actually transfer energy to each other. It's too chaotic, there's too much going on. So all we say is that in the end, right, something will happen, and that something is basically random, right? So the hotter body had more energy packets, more energy pieces, and then when it connected with the other body that had fewer, it tended to move the pieces towards the one that had fewer, right? That's what's going on. I guess you could use cows too. If you have two pastures, right, separated by a fence where cows can cross, what's more likely to happen? Are the cows going to be on one side or the other? Well, cows like to group together. So say they're goats. Goats don't like to group together. What's more likely to happen? The most likely occurrence is that the goats are going to spread out, right? Unless like there's some pressure to push them together, but assume there's not. Okay, so they're going to spread out. Okay, that's basically what's happening. Okay, my goodness, my dog is freaking out. Let's scale this up into real world numbers. Okay, first of all, checkerboards are tiny. You take like this leaf petal here, right? Let's see if we can focus on that tiny little piece of matter there. Inside that piece of matter because it's a solid and has liquid components too, but there are tiny pieces that are moving around, okay? And because of quantum mechanics, there's only so many modes, so many, you can actually count the ways that those particles can vibrate, okay? That's what the quantum means. Quantum means counting mechanics, right? So the thing is though, is that little tiny piece of matter has an incredible number of particles and ways to arrange energy among those particles, right? And we're using numbers like a mole. If you don't know what a mole is one, basically 1 followed by 23 zeros, okay? Each time you add a 0, you're multiplying by 10, right? So it's 10 times 10 times 10 times 10 times 10 times 10 times 10, 23 times, okay? That's a huge number, okay? And then we're talking about the temperatures that you're used to, the amount of energy that's in that petal, that little tiny piece of matter, right? And we're talking like moles of energy, right? Packets. And then we take these two systems and we connect them together so that they can transfer energy between them. What's the most likely outcome? And the answer isn't just like, well, it's going to be about equal energy between the two, you know, give or take. It's like, no, it's going to be equal, because any deviation from that, even the smallest deviation from sharing the energy equal, is going to be so highly unlikely and improbable that you will never observe it in this universe or 100 million, billion, trillion universes, okay? It will never happen, right? And so we say that the energy will flow because of random chance from the one that has more energy to the one that has less, okay? And the energy allocates itself. The energy allocates itself. You are crazy, doggy. The energy allocates itself in such a way that it kind of spreads out like a fluid. And this is why early on in the study of thermodynamics, physicists thought that there was this thing called caloric. It's like a liquid that would spread out, right? Because that's the only theory that made sense. And indeed there is, it's energy. Now, a key thing you need to think about, this is important, is different kinds of matter, right, can store energy in different ways, okay? And when I say in different ways, it's not like, oh, you know, this one has like, you know, this drop of water has like 6 more ways to store energy than that other, you know, drop of carbon dioxide gas or whatever. You know, I'm not talking like that. So each particle inside of the matter has like, if it's just a point, right, it can vibrate left and right, it can vibrate up and down. Let me do this, up and down. It can vibrate back and forward, right? So that's 3 ways it can vibrate. And any possible vibration is a combination of those 3 modes, right? Once you add a second particle to it, well, now you can have it spin. Spin this way, spin this way. That's 2 more modes of vibration, right? And the reason why I'm not considering like the point particle spinning is because it's a point. Spinning doesn't mean anything to it, right? And so the particles that are aligned in a line, right? The diatomic molecules like nitrogen gas, hydrogen gas, they have 2 additional, right, modes of vibration, okay? This is important because that's what, 66% increase in the number of ways to move. So in a drop of monatomic, so like single atom, like helium gas, right, versus hydrogen gas, right? The hydrogen gas has 66% more ways to store that energy. What that means is the energy is more likely to flow towards the hydrogen gas if they had equal number of energy, until that the hydrogen gas has 66% more energy than the helium gas, right? That's how they equalize, right? Its checkerboard is so much bigger. It's 66% bigger than the helium gas. Now you add a third particle, third atom, right? So you have something like water, and water, remember, it has like Mickey Mouse ears, right? So not only can it spin this way and this way, but it can also spin this way. So now we have another mode of vibration, right? And so water molecules above monatomic particles has twice as many movements, and above diatomic molecules, it has only, 1 out of 5. So 20% increase, okay? You got that? That's important, because the next part is gonna blow your mind, okay? Water, the same amount of water will hold more energy at thermal equilibrium. So when everything is stabilized, all the temperature stabilized, the water will hold more energy than hydrogen gas, and especially more than helium gas. And we can go and we can look at these different matters. We can measure, right? We can measure precisely how much energy each of these things holds, right? And so we can predict exactly what will happen when we bring different substances into thermal contact with each other, okay? This is the key point. When there is a thermal exchange of energy, we call heat. When you're referring to heat, that's the natural movement of energy from something hotter to something colder, okay? The energy moves in one direction only, net, okay? It never moves backwards, okay? So when people draw pictures, there's some feedback there. The dog can smell it. I don't know why he just doesn't go eat his own food, but anyway. So when they draw pictures showing the heat coming from the earth and being reflected back to the earth, that is utter nonsense. It means nothing. Heat is not that kind of thing. Heat moves from a warmer body to a colder body. Maybe they mean that the heat radiates from the earth to the atmosphere, and the atmosphere absorbs it because the atmosphere is colder than the surface of the earth, which it is, okay? But they cannot possibly mean that the atmosphere will then transfer heat to the earth because the earth is warmer. The surface of the earth is warmer than the air. That is not possible. It's not physical. It contradicts everything we know about how thermodynamics works. And so if you ever see a picture of somebody showing heat rays coming from the earth, reflecting back from the atmosphere to the earth, you can tell them that that violates the second law of thermodynamics, okay? It never happens that way, right? It will never flow from the atmosphere to the earth. Now, if you want to get into a detailed discussion of what's actually going on, okay, yes, carbon dioxide has a difference opacity to certain wavelengths of light than other particles. Okay, it's different. However, the energy transfer is due to a change, a difference in temperature. Right? The fact that carbon dioxide blocks certain frequencies of light and allows other frequencies of light to pass through does not change the nature of the checkerboard game. Right? It has no bearing whatsoever. Okay. The last little bit here. Okay. When the Earth emits infrared light due to black body radiation, because it's warm, every object that has any kind of energy emits some kind of black body radiation, right? The atmosphere can either allow that to pass or it can absorb it. That's the only two options, right? If the atmosphere allows it to pass, that energy goes up to space. That's it. Okay. Am I talking about checker pieces and checkerboards? Am I talking about entropy? Am I talking about heat? Am I talking about temperature? No, I am not. Okay. I'm just talking about one particular kind of energy and how it flows. Okay. If the atmosphere absorbs that infrared light, then either the atmosphere retains it, right, which might be due to the temperature difference between the Earth and the atmosphere, or the atmosphere will let it go. Okay, send it off to another system. Where does it send it off to? To space or to Earth? The answer is the atmosphere can't tell which way is up. It can't tell which way is up. It emits the radiation in any direction. Okay, and so that means that it doesn't matter whether the radiation was coming from the Earth or the space. The atmosphere radiates it equally in all directions. Okay, that's just simple logic exercises. Okay, but the key takeaway point here is that heat does not refer to any kind of energy transfer between two systems. It refers to only the energy transfer due to a difference in temperature. And the reason why there's a difference in temperature is because one system has more energy density per the number of places where that energy can go than the other. That's all it is. Okay? That's all it is. That's everything you need to know about temperature. So if people talk about heat rays, you can shut them down and say that's not how heat works. That's not heat. If they say, well, what about absorption lines? You're like, what does that have to do with heat? What's the connection? And they have to sit down and say, well, you know, the energy's allocated, blah, blah, blah. And you're like, well, if the energy isn't transferred because of a change in temperature, the difference in temperature, then it doesn't matter. It's not heat, right? If the energy is transferred due to that, then it is heat. Does it matter what form the energy transfer takes? The answer is absolutely not, okay? Now, you can obviously change how the two systems interact. You can change the relaxation time. That's how long it takes for the temperature to stabilize between them. We know that we can take ice and stick it in a cooler, and the ice will melt a lot slower than if you leave it out, right? All you're doing is you're restricting the speed at which the energy flow can happen. That's it. Okay. And as far as we can tell, in every measurement, carbon dioxide gas conducts heat slightly better than nitrogen and oxygen gas. So if you were to raise the carbon dioxide levels of the Earth, which, by the way, there is so little carbon dioxide in the atmosphere, it's a trace gas. You can barely detect it. I think it's like 4 parts per million or something like that, right? So out of every million molecules in the atmosphere, only 4 of them is carbon dioxide, okay? It's like right up there with like argon, okay? If you were to double the amount of carbon dioxide gas in the atmosphere, it would lead to a slight decrease in temperature due to the more efficient heat transfer that carbon dioxide does, okay? However, that change in temperature would not be measurable on any device that anybody's ever created to measure temperature. It's not possible, okay? You'll never detect it, certainly not with the fluctuations in temperature that happen all the time on the surface of the Earth. And in the time that I've been talking to you, the air has probably risen 2 or 3 degrees, okay? What do I care about a 0.0004 degree change in temperature? It doesn't matter. All right, guys, have a great day. Bye-bye.